Great. So expectedly, we did not cover everything that we might have covered in this class, but I really did want to make sure that we sort of got through at least the bulk of this theorem, at least enough to sort of come away with it, understanding how it goes. And there are a lot of moving parts. It's very much like a classification theory kind of proof, where you have an object that you're constructing in stages, which has several conditions that it needs to satisfy, and all those conditions are kind of complicated and combinatorial. So for that reason, I did something which is a bit abnormal, which is that I wrote most of the lecture beforehand. So what I did was I tried to write everything that could exist as preliminaries or as easy reductions. And then when we get to the heart of the argument, we'll slow down, we'll do it carefully and slowly. So, okay, the main theorem today is going to be a characterization of NSOP2, which is the same thing as NTP1. So recall, this is the tree property that says you've got paths are consistent and incomparables are inconsistent. And we want to try to give a definition of that, which doesn't talk about trees. So somehow, if you can do that, then it somehow tells you that you found the tree in a natural setting. You know, like you didn't have to talk just about trees to find trees. You could find it in some other context. And I will say that, you know, we've had many instances of this kind of theorem, like in NSOP1 or in NTP2, we had theorems that talked about, that characterized NTP2 in terms of, you know, dividing or forking or something, where the tree was not present, but it was found. And I think that interpretations of NTP1 or NSOP2 that have that shape are few and far between. So, you know, the more we find, the better, because then we'll understand the property better. At the moment, I would say that NSOP2 and NSOP3 are extremely mysterious. We don't really know what they mean. So this is one theorem that sort of gives an indication that perhaps there's something to be said there. So, okay, the theorem today will say that the following are equivalent. One is that T is NSOP2, and the second is that if you have a set of parameters, A, and you have a family of higher formulas over A, indexed by the ordinal alpha. And notice here that the formula in each one of these higher formulas is the same. So the types are changing, but the formula is the same. So it's Pxy in all of those formulas, but the P's are different. Those are varying as I varies. And we have this property that for some K, if I is less than J, then phi Pi is K contradictory to phi Pj. So if I look at two types in my sequence, the first one is going to be K contradictory to the second one. So suppose you have a family like that. So this like very contradictory family, then it follows that the length of the sequence of higher formulas is small, bounded by the size of the parameter set plus alt 0. So if A is finite, then actually you can extract a finite bound from the proof on how long the sequence can be, but basically we won't care. I mean, we'll just say that it can't be bigger than the size of the parameter set when the parameters are infinite, for example. Okay, so this is kind of interesting. You can think of this as a kind of an amalgamation fact. So before we had things like the independence theorem, which say that, you know, under certain circumstances, if you have two types over different parameter sets, you can put them together. And what this is saying is that suppose you have a family of types which are higher formulas. Suppose you have a big family of higher formulas over your set, then there have to be two that you could put together. Because otherwise you'd find a K inconsistent, or, you know, a K contradictory family, something like this. I mean, you can think of it vaguely like this. They can't all be one inconsistent, because if they were all one inconsistent, then that would give you a very long family that's pairwise one inconsistent. That tells you that you must have SOP2. So the fact that they can't all be one inconsistent tells you that you can find instances of these two higher formulas and put them together. They're consistent together. So it's like an amalgamation fact, although, you know, how to see it as an amalgamation fact is kind of tricky. All right, so one of these directions is easy, and that's going to be the one that says that if you have SOP2, then you have a big family of contradictory higher formulas. So let's do that one first. So the easy direction just says, okay, suppose you have that phi xy witnesses SOP2. So what does that mean? You have a collection of tuples indexed by the complete binary tree, a eta, eta in 2 to the less than omega, and paths are consistent, and incomparables are inconsistent. So suppose we're given that configuration. What we will do is we will take the set A to be the parameters that appear in that tree. And then for each path in my tree, I'm going to take a non-principal ultrafilter that concentrates on that path. So because it's non-principal, that will say that any in segment of that path is big. So it's like the Fréchet filter it extends the Fréchet filter on that path. Okay, so it says everything sort of outside the path, everything disjoint from the path is small, and the path itself is big, and all of its in segments are big. That's what it will say. All right, so then for each path, we get a type. Oh, I didn't say what the type is. I should have said that. So I get this ultrafilter. And what we will do is we will define P eta to be the average type along D eta over the monster model. So you get some global A finitely satisfiable type by taking the average along this ultrafilter. And what does that look like? Well, if you look inside your model, or sorry, inside of A, so here we've got A, and I've got these paths inside of A. Now, suppose I take a Morley sequence in P eta over A, then that is going to be consistent. If I plug those parameters into phi, that's going to be consistent because it comes from a path, and that path was consistent. Additionally, if I take two different paths, then they diverge at some point. So after a finite initial segment, all of the elements past that finite initial segment in those paths are incomparable with one another, pairwise. And that means that if I realize a Morley sequence, in one of the types, or even once, if I realize one of the types, then what formulas go into that type, the things that are true for almost all tuples in that path, and almost all tuples in that path are incomparable with almost all tuples in the other path. So the two realizations will be incompatible with one another. So it's very easy to check that just using the definitions of average type and the conditions on the sequence we took, or the tree we took, these will be pairwise one contradictory. I should have said contradictory, not inconsistent. One contradictory, which is great. So that gives you one direction. Notice now that it doesn't actually matter the order in which I take them. They're contradictory going both ways. Cool. So that gives you one direction. Is that good? Does that make sense? Okay. So now we will go the other direction, which is much, much harder. So we're going to have a few easy reductions, and then we're going to come to like the main definition, and we will try to get through as much of it as we can today. So the first thing that we'll do is we'll use what we did last time. So last time we proved that SOP3 is equivalent, in SOP3 is equivalent to higher contradictoriness of higher formulas being symmetric. So if VP is contradictory to CQ, then CQ is contradictory to VP. That's what we proved in an SOP3 setting. Okay, so what we're going to do now is we're going to assume that we have a really long collection of higher formulas where if I take the ith one, it's going to be k contradictory to the jth one when I is less than j. And I want to produce SOP2. Now, if my theory has SOP3, then we argued last time, or I sort of sketched it out loud, that you can build these intervals and find SOP2. So SOP3 implies SOP2. So if my theory has SOP3, I'm done, right? I'm not in an SOP2 context because I want to produce SOP2. So if my theory has SOP3, then I'm done. So I can assume for simplicity that I'm in the case that I'm in an SOP3 theory. So for the purposes of the proof, I can assume SOP3, and therefore I can assume that contradictoriness of higher formulas is symmetric. What does contradictoriness mean? Contradictoriness says that if I have infinitely many realizations of one Morley sequence, and I have infinitely many realizations of my other type forming a Morley sequence over the other thing, then that collection of infinitely many formulas is inconsistent, right? Now, by compactness, like what compactness will tell me is that if whenever I look at I less than j, I think it froze. Hopefully it's still good. Whenever I look at I less than j, if I get something which is inconsistent, k inconsistent rather, then there's going to be some in k, so that I'm in k contradictory the other way. Because otherwise, if I wasn't in k contradictory for any in, then I could take longer and longer sequences and be k contradictory one way and then not contradictory the other way. So compactness will tell me there has to be some bound. And in fact, you can check that it only depends really on the formula, not the type. And the fact that the formula is fixed here tells me that there's going to be some in k that works for every I in j. So because I knew that phi pi was k contradictory to phi pj, it's going to follow that phi pj is in k contradictory to phi pi. And this is kind of a subtlety, right? You might be tempted just to say, okay, k contradictory one way implies k contradictory the other way. But it doesn't actually say that, because contradictory uses this whole infinite tuple. So compactness just gives you this, that if there's a finite direction going one way, there has to be some finite amount going the other way, although those finite amounts can differ. But we had these reductions that told us that if I have a formula, which is a higher formula, then I can replace the formula with some conjunction of instances, and I can replace the type with one of its tensor powers, and that will give me another higher formula. And I can reduce the amount of consistency from k to 1. So what I can do is I can look at the maximum of k and nk and replace my formula with a conjunction of that many instances, and replace my type with a tensor power that many times. And now what I have obtained is a family of higher formulas, which I will call phi p alpha. So I'm not going to change the formula's name because it's nice to call it phi, though we might have had to make a change. I obtain a collection of pairwise one contradictory higher formulas. And I'm going to assume that these are indexed by lambda, which is going to be bigger than what my bound predicted, because I'm improving the contrapositive, right? So what did my bound say? My bound says that the family shouldn't be bigger than the size of a plus all of 0. So I'm going to assume that I have a family indexed by the successor of that in order to produce SOP2. Okay, so that's the first reduction. We can assume that our witness to not 2 is actually a family of pairwise 1 contradictory higher formulas, which go both ways. So they're contradictory in both directions. Great. Okay, so that's the first reduction. The second reduction is really just like compactness applied to the definition of SOP2. So SOP2 says you have some infinite collection of tuples indexed by the complete binary tree, such that paths are consistent and incomparables are inconsistent. But because that's in a single formula, if you have that not for the complete binary tree, but let's say the binary tree up to size n for every n, then by compactness, you can find it in a collection of infinite tuples, possibly in a different model. And then you've shown that the formula witnesses SOP2 with perhaps a different set of parameters by a compactness argument. This isn't so hard to see. You can write down a type in the variables y eta for eta in 2 to the less than omega, and write down a collection of formulas that say, okay, if I take finitely many instances along any given path, those are consistent with one another. And if I take 2 incomparables, those are inconsistent. And that type will be finitely satisfiable if I can find arbitrarily large approximations to SOP2. And so compactness tells me it really just suffices to show that for arbitrary n, I can find an approximation to SOP2 of height n. So that's what we will do. We will fix n, and we will try to find an approximation like that. And n is going to be fixed once and for all for the course of the proof. It's going to be an arbitrary natural number, and we just want to find an approximation to SOP2 of height n. Okay. Now we come to the definition of frontier, which is very sensible. So suppose you have a subset of 2 to the less than n, and that subset is downwards closed. So it's a subtree. Then the frontier is just the collection of nodes in that tree that do not have both of their successors. So we're in a binary tree. So anytime you take a node, which is not at the top, so its length is strictly less than n-1, and one of its successors is missing, then it's in the frontier. So these are just the things that need to be taken care of. So you can imagine that like we're going to be building up our approximation step by step, and we're going to start with maybe the empty node, and then from there we're going to try to add successors. And then to the things that we add, we're going to add their successors. We're going to keep iterating this until we run out of nodes. In the complete binary tree. And our construction will be the frontier. And for elements, I'm going to b bar alpha, which is my name.
Nick, you're muted.
Okay, thank you. That was quite strange. And what I said is I'm gonna try to pin myself, because the last time that I lost connection in the lecture, it turned out to just think that James was king of the meeting. And I want to avoid that if possible. I want you all to admire my face. Okay, so let's share screen. I wonder what happened though. Okay, so everyone sees it, we're good? Okay, fantastic. Sorry about that. This sounds like we're in the Stone Ages or something, but at the internet that I have in Missouri has the property that whenever it rains, the internet is bad, which I can't believe that that's a thing. Like the internet really is a series of tubes. It's crazy. Okay, so anyway, what I was saying is that we fix once and for all a Morley sequence in each one of our types, which we're going to call b bar alpha. And now we're going to use that as part of the data of what it is to be an approximation. And an approximation is called that because it's going to be sort of like what we're building along the way to trying to find this witness to SOP2 up to height n. Okay, so an approximation is going to be a pair, A eta, eta in lambda, and U eta, eta in the frontier of lambda. And so you can think about the A etas as like the parameters that we're trying to build in our tree. And the U eta is going to be some additional data that tells us how to extend. So we're going to have these things attached to the frontier, and we're going to sort of use those U etas to guide our construction of replacing any gaps with new parameters using the information that the U etas contain. So the three conditions that we have are, okay, one says that lambda is a subset of 2 to the less than n, which is downwards closed, so it's a subtree. And just to order our construction, we will say that if eta 1 is in lambda, then eta 0 is in lambda. So that means that you're sort of going to handle adding a new node to the frontier in a lexicographic way. I mean, you're going to sort of prioritize 0. So, I mean, whenever you come to a node in the frontier that needs attention, needs a successor, then you're going to add its 0 successor first. Okay, so that's just to make a choice. The second thing is that it's an approximation to SOP2 as we want. So you have this collection of tuples. I'll mention an important fact, which is opaque in the published version, but it's an important feature of the argument, which is that these tuples are from A. You're going to find them inside the set A. And it's going to have the property that if you take a node in lambda and you look at the initial segment of a path, all the initial segments of lambda. So you just look at, or sorry, eta. You look at eta and you look at all of the initial segments of eta. That's like a piece of a path, and you want that to be consistent. And if you take two incomparables in lambda, you want those to be inconsistent. So this is saying that it looks like SOP2 for the parts that you see. Paths are consistent, incomparables are inconsistent. Okay, and then the third condition is where we get into something that's kind of technical. And this is where you start to see how it's going to be useful to have these U-etas around as information to guide our construction. So the U-etas are a collection of disjoint subsets of lambda, each of size lambda. Recall that lambda was the successor of the size of A, assuming A is infinite. So it's an uncountable set. So you have this uncountable collection of uncountable sets, and you have two pieces of information. So the first piece of information says that if I take something in the frontier, and oh, I wrote eta, but I meant nu, and let me fix this. This is not written quite right. So I take something in the frontier, and I look at all of its proper initial segments. So because it's on the frontier, that means that all these proper initial segments are inside of lambda. And those things have to be consistent. But what I want is that they're consistent with an initial segment of the associated Morley sequence as well. So somehow the way you should think about this is that like this Morley sequence is finitely satisfiable inside of A, right? So you have part of the sequence which is outside the model, or sorry, outside of the set, and then you have something which is inside the set. And what you want to do is you want to take something from the sequence and put it inside the set, preserving certain properties. So like one of the properties that you want to preserve is that you have consistency. And because these are higher formulas, you know that all these paths are consistent, but you don't know that they're sort of consistent when you move them inside the model, especially preserving all the other stuff. So what this is saying is that somehow, if you're building a path inside the set A, if the path has length k, then you need to be able to extend it n minus k many times from the Morley sequence. So you have that much energy left in the Morley sequence above to pull things down and to get a consistent path. So that's for like path consistency. All right, and the second thing is like pirouette, saying that incomparables are inconsistent. Although we have to jazz it up a bit just to talk about this context. So if we take something which is the frontier, let's call it eta, and we take some alpha, which is in U eta, and a nu inside lambda, and nu is not an initial segment of eta. So in particular, does this force them to be incomparable? I suppose this implies in particular that they're incomparable. Good. Then we have that phi b alpha 0, phi x a nu is inconsistent. So you think about the elements of this Morley sequence associated to alpha in the eta set as being a candidate for the element you want to add as a eta. And so what should it satisfy? It should satisfy consistency along paths, and it should satisfy inconsistency along things that it's incomparable with. And so that's going to be the basic condition. Okay, so these three things are the conditions for approximations. And that took 25 minutes, and now we're just going to try and prove the construction from there. So I'm glad we did this. I think it sped things up. Also, these are technical, and I don't really trust myself to say them accurately from the contents of my brain. So so it's good that I wrote them down. Okay, any questions up to this point? No? Okay, so we're going to prove two subclaims. One claim will say that an approximation exists. There's at least one. And then the second one will say that any approximation, which is not indexed by the full binary tree, can be extended one step. And then that suffices. Then we have one approximation, we extend it one step, we extend it one step, we extend it one step, we extend it one step. You do that until you run out of space, and then you're done. So that's the plan. So let's do the first claim. So claim 1 says there is an approximation A eta in lambda, or sorry, that's not how you write that. A eta in lambda, U eta in the frontier of lambda, for lambda as equal to just the downwards closed subset consisting of the root node. So this is going to be our starting point. We just want an approximation that begins at the bottom of our tree. And then we'll worry about extending it secondly. So this one's not hard. So proof of claim. So for any lambda, sorry, for any alpha less than lambda, we know because phi p alpha is higher over A, the type of B alpha n minus 1 over A B alpha less than n minus 1 is finitely satisfiable in A. That is something we were told, right? It's part of what it means to be a higher formula, that each one of these types is finitely satisfiable inside the set. And additionally, it's true that there exists an X such that if I take the conjunction over all I less than n, phi X B alpha I, there is a witness like that. Why? Well, because you're told that if you plug in all of the elements of a Morley sequence as parameters inside of phi, that gives you something consistent. That's part of what it means to be a higher formula. So this is true. So there is some C alpha in A with exists X and I less than n minus 1, phi X B alpha I, and phi X C alpha. What did I do? I just took B alpha comma n minus 1 and I moved it into A. And why can I do that? Because I have a single formula and I know that my type is finitely satisfiable. So what does it mean to be finitely satisfiable? It means that whenever I have formula in the type of B alpha n minus 1 over A B alpha less than n minus 1, I can find a witness for that inside the set A. And so here's the formula, and C alpha is going to be the witness to that. Great. So as lambda is bigger than the size of A, strictly bigger, by the pigeonhole principle, there is some element that we're going to call A empty set in A, and a set U, subset of lambda of size lambda, such that what happens? Well, if alpha is in U, then C alpha is equal to A empty set. Okay, so for each alpha, we picked an element of A but there are only cardinality of A many elements of A, and we have cardinality of A plus many elements chosen. So a lot of our choices had to be the same. In fact, lambda many of our choices needed to be the same. And so we can find some subset of the indices called U and go from there. Great. So now we will define A eta, eta in lambda, U eta, eta in the frontier of lambda, just to be, okay, you have the tree that just consists of a empty set, and you have the sequence just consisting of U. And that works. So why does that work? Well, this condition here is the one that says that I can still continue with my sequence in -1 many steps. So I have one element, and I can continue with my sequence in -1 many steps. Now, the second condition for an approximation never kicks in, because if I take an element here and an element here, sorry, an element here, this condition is never satisfied when nu is the empty node, because the empty node is an initial segment of everything. So condition B is trivial. And okay, condition B here is also trivial because I have no incomparables around. And condition A is satisfied because we know that exist X phi X A empty set is true. And it's downwards closed. So that satisfies all the conditions. Great, so that's the proof of the claim. So now we need to do the hard part, which is extending one step. So claim 2. So suppose X sub tilde. I don't know how to indicate like a bold X. So like I've seen Marianne give talks where she'll just write a tilde underneath. So that means bold. Okay, read it however you like. I might say X bold. Okay, so suppose that this is equal to X bold, eta in lambda, U eta in the frontier of, sorry, lambda X bold. Sorry, I want to sort of mark the dependence on X for everything because it'll be convenient going forward. Okay, this is an approximation. With lambda sub X bold being a proper subset of 2 to the less than n. So we haven't completed our tree yet. We want to be able to extend it one more step. So then there is an approximation Y bold extending X bold with lambda Y bold of cardinality strictly greater than lambda X bold. Okay, now I haven't said precisely what I mean by extend, but I take it you can imagine, right? So what should it mean? It means that the collection of tuples indexed by the tree should extend the collection of tuples indexed by the first collection. And also that, maybe I should have said it actually. So whenever you have two things which are in the frontier, which are in common, then the U etas can shrink. So I mean, because these have certain conditions, as I extend, I might lose certain candidates. So the U etas might shrink, but they still have size lambda. So I might make those sets a bit smaller, but they're still going to be big. That's what it means to extend. All right, so for simplicity, we will write x bold is equal to a eta, eta in lambda, u eta, eta in lambda, or sorry, frontier lambda. Okay, so now pick eta star, which is in the frontier of lambda. So we know that we haven't taken up everything, so there has to be something which doesn't have both of its successors. So eta star is going to be our element of the frontier, and what we will do is we will let c star equal eta star concatenated with 0 if eta star concatenated with 0 is not in our tree. And otherwise, we will take it to be eta star concatenated with 1. So recall that we sort of set it up so that we handle things in the lexicographically prioritized way. So if I have something in the frontier, I want to first add 0, and after I've done that, then I add 1. So c star is going to be the element that we want to define. We want to define a sub c star. That's our goal. So we will also let k be the number in minus the length of eta star. Recall, this is like how much of our Morley sequence we want to be consistent with our path. So at each stage, like if I add 1 element to my tree, I need to have n minus 1 elements in my Morley sequence consistent with it, because those are the candidates for my path. If I have 2 elements in my tree, I want n minus 2 many things in my Morley sequence consistent with that path, and so on and so forth. So if I know that eta star is the element on the frontier, then I need to be able to extend k many steps left. Okay, so that's just for notation. So now what we will do is we will fix an arbitrary sequence alpha bar. It's going to be alpha eta, eta in the frontier of lambda, such that alpha eta is an element of u eta. So I don't know if this is helpful, but I'll draw sort of the picture that's in my head. So now if we look at this picture, we can ask, okay, what is the frontier? So let's suppose we want to build up to one more step. So we have this is in the frontier, and this is in the frontier, and these two are in the frontier. So I mean, assuming that I want to build something of height 3, let's say. So to each one of these things, I associate some set. And you know, let's call this like eta 0, eta 1, eta 2, eta 3, and then I pick sort of an arbitrary choice, alpha eta 1, alpha eta 0, alpha eta 2, alpha eta 3 from each one of these sets. So these are actually just ordinals in lambda, because the u etas were sets of size lambda, just disjoint sets of size lambda living inside of lambda, collection of indices of types. And the idea, you know, in each one of these types, like if I look at this alpha 0, then I know that attached to alpha 0, there's some Morley sequence in p alpha 0. And I know that if I take this element and this element, then there have to be, you know, some number of elements inside my Morley sequence which are consistent with it, like that. So that's the consistency condition. And then of course, then you have inconsistency conditions saying like this and this are going to be inconsistent, like this and this are inconsistent or something. So there are conditions like that, but this is somehow the picture you should have in your head, something like this. You have sequences, or let's say sets attached to each one of the elements on the frontier that sort of tell you how to extend. Great, so we made this arbitrary choice, and we're just going to reason about this arbitrary choice for a moment. So next, pick some beta, which is an element of U alpha eta star, but is not equal to alpha eta star. So recall one of these was like our special one. Let's say this one is our special one. And then we're going to pick some random other element, which is going to be beta star living there. Beta star. I guess we don't need the star. Maybe we just call it beta. Okay, so by condition 3a, we know that for every alpha in U eta star, there exists X such that conjunction for L less than the length of eta star, phi X A eta restricted to L, and the conjunction of I less than K minus I, phi X B alpha I, and phi XY is in the type, well, it's in the type P alpha eta star of Y, because this is true of the next element of the sequence, which is realized by this element. So this formula, which uses the variables Y, is in this type. Additionally, by 3b, for all nu in lambda with nu not an initial segment of eta star, we have for all alpha in U eta star, not there exists X such that phi X A nu and phi XY. This is also in the type P alpha eta star, because that's what it says. It says that if I look at the Morley sequence, it's inconsistent, and that, you know, this type is just the type of the Morley sequence. I mean, it has parameters in A, so it's got to be there. So likewise, we have, I shouldn't have a models, because I'm actually describing a formula in the type. So we have not exists X phi X B alpha eta and phi X, like I guess I should say 0, and phi XY. This is in the type P alpha eta star of Y. So this is because of condition 3b also. This says that they're inconsistent. Or no, sorry. This is by the one contradictoriness of the family, right? Like, what does the family say? I mean, what does it mean to be one contradictory? It says that if I realize P alpha eta star over any one of the other realizations of one of the other types, then those two instances are inconsistent. And so that means that this formula in particular is going to be in the type. That just hard codes what that says. Okay. Great. So wait. Something is a little confusing to me. No, I guess this is right. Yeah, good. So this is just for all the other stuff. So right. So this says that here we get inconsistency with the stuff that we want, and here we have inconsistency preserved with the things that we haven't fixed yet. And so therefore, the conjunction of all these formulas is a formula in P alpha eta star of y. Right? Like if you, if you have finitely many formulas in a complete type, then their conjunction is also in the type. That's not so deep. So it's satisfied. So this is satisfied. By C alpha bar beta in A. Great. So by the pigeonhole principle, there is some C alpha bar and W alpha bar, which lives inside of U alpha eta star, take away alpha eta star, with W alpha bar is equal to lambda. Oh, by the way, I think I realized what I did know. I think I see what the problem was. Here, this really should have been about B beta. Using the beta that we picked. So that's why it matters that we had this beta around. So, okay, sorry about that. So we have this. So this W alpha bar says lambda, and you know that for every beta inside W alpha bar, C alpha is equal to C alpha bar beta. That's again by the pigeonhole, just because you have lambda many options for beta and fewer than lambda many choices for the tuple C alpha bar beta, but that still depends on the choice of alpha bar. And now you're going to do something kind of silly. So for each gamma less than lambda, let alpha sub gamma equal A gamma eta, eta in the frontier, such that what? You want that A gamma eta is equal to the minimum among U eta take away gamma. The point is just that now you get lambda many things. For each gamma, you get a different thing. And they all have to be, I mean, the pigeonhole principle will give you something where these are all distinct. And you know that you're going to have lambda many choices for each one of the coordinates. Because if any one of the coordinates was fixed, or even bounded in lambda, then you'd eventually reach a gamma where you had to take it away. So this is just like a way of using the pigeonhole principle to make sure that you don't end up having many tuples, but like one of the coordinates are all the same. This is just a device to be able to use the pigeonhole principle to get a collection such that the coordinates are all different. or I mean, they can overlap, but they can't overlap much. I guess that's the point. Okay, so then by the pigeonhole principle again, there is W contained in lambda such that C alpha bar is equal to C. Well, okay, in C, so in A, such that C alpha bar C is equal to C for all alpha bar gamma. So alpha bar gamma for all gamma in W. Great. So now we'll just define an interpretation, or sorry, an approximation y tilde is equal to A eta, eta in lambda y, U eta, eta in the frontier, by, okay, what should you say? Well, you want to say that lambda y is equal to lambda x together with this new element, eta star, to a y eta is equal to ax eta for all eta in lambda x, and a y eta star, or sorry, xi star. Wait. Sorry, I said eta star, but that was already in there. We wanted xi star to be the next thing. So xi star is going to be this element C. 3 is you're going to make u y eta is equal to alpha gamma eta for gamma in W for all eta in the frontier of lambda, take away eta star, and then you have some additional casework because you don't know how to define it on the rest. So this is just the first condition. Then you have B, which says, okay, what if the length of L C star is less than n minus 1? Then it becomes part of the frontier because it doesn't have its successors. We just added it. So then we set U y C star is equal to alpha gamma eta star. So these things become our new elements. Gamma in W. And if eta star has one successor in lambda x, then we're done. Because now we've added the other one, namely we added C star. But otherwise, if it needed two successors, then it's still in the frontier. Otherwise, we set U y eta star is equal to W gamma for gamma less than lambda, and such that C alpha bar gamma, oops, is equal to C. Okay, so that's the second claim. And obviously there are a lot of checks that you have to do to make sure that this still works, but I think intuitively it's clear, right? That like, how did we choose these things? We chose them so that we satisfy the first type. And what did the first type say? It said that we can continue along the paths. We chose them to satisfy the second type, which says that you're inconsistent along everything you've seen so far. And then we satisfy this third condition, which says that you're inconsistent with the stuff that you're adding to the frontier, because that's the whole point of changing the frontier to be one of the, the shrunken version of one of the old U etas, because we checked that we were still one inconsistent with all that stuff, and that uses the one inconsistency of the family. So all of those things are things that we have to maintain, and using finite satisfiability plus the pigeonhole principle, we can continue our approximation one step. We continue until we're out of frontier. And then we hit the California coast, we're happy. Okay, so what did we do? We characterized SOP2 in terms of this kind of viewed distantly amalgamation fact. And that means that we've proved deep and beautiful structure theory for NSOP1, for NTP2, for NSOP2, and also for simple. All of this building on various tools that we developed from the very beginning about average types, about indiscernible sequences, and playing lots of games with those. So this is kind of a grab bag class, but hopefully you saw that there are a few things which are working in common, namely extraction of indiscernibles, invariant types, and thinking about forking and dividing in the ways that formulas can collide or overlap. And so I don't have much to say in the way of like synoptic overview, but all of these things are things that I really love, and it's been a pleasure to share them all with you. So thank you for following along. And I'm going to miss this class, so it was fun. That's it.